59. Well, hello everyone. Welcome to a new installment in the traditional NAGRAM seminar. It's just becoming. I hope it's becoming. We hope it's becoming a tradition. I'm very excited to introduce today's speaker. This is Ping-Hsuan Tsai. So Ping-Hsuan got his PhD from University of Illinois with Paul Fisher, and he joined this year. He joined Virginia Tech as a postdoctoral scholar, and today he's going to be talking about something new, I guess, for our communities, that turbulent channel flow. So time relaxation, reduced order model for the turbulent channel flow. Ping-Hsuan, the floor is yours.
Okay, thank you, Chang, for the introduction, and thanks for the organizers for the invitation. Today, I'm going to talk about a time relaxation reduced order model for the turbulent channel flow. This is a collaboration with my PhD advisor, Paul Fisher, and my postdoc advisor, Tsai. So our group is interested in fluid thermal analysis, which plays a critical role in many engineering applications for design and analysis. For example, when you're designing a nuclear reactors, requires you to understand the rod bundle thermal hydraulics. And for nuclear reactor safety, nuclear engineer have to know where is the thermal fatigue happens in the pipe and to avoid the pipe failure to enhance the safety. Or you want to design the wire coil to enhance the heat transfer to further remove the heat in the accelerators. And we like to realize those design analysis through CFD. And thanks to high performance computing and advanced algorithm, we're now able to solve problems with unknowns range from thousands to billions. So the unknowns here, the notation we use is a script n. And you can solve, so now we can solve a 2D model problems on our laptop and can probably solve a small 3D problem with powerful GPU like M2 Pro. And you can solve a larger problem like 3D flow past a cylinder, turbulent pipe flow or channel flow on workstation and cluster. And for 3D industrial applications, we're capable to solve it now, like pebble bed simulations and rod bundle thermal hydraulic and T-junction. So we're able to do those calculations from 2D to 3D with the high performance computing and advanced algorithm. However, when it comes to multi-query applications, CFD can be expensive because it requires hundreds of high-fidelity simulations to do those routine analysis and design, uncertainty quantification, and real-time control decisions. So we need accurate but rapidly solvable models, and reduced order model can provide such a tool. So in this talk, we'll be focusing on projection-based reduced order model. So I assume most of you are familiar with this. So I'll go through it real quick. So the idea is to take the high fidelity data or the so-called for the model data, which there's billions unknowns, and run through the proper orthogonal decomposition or SVD to get the reduced basis functions. And with Galerkin project, we do Galerkin project Navier-Stokes equation onto reduced space, spanned by those reduced basis function that we got from the POD. And we derive the Galerkin-based reduced order model, which is called GROM. And here the A and B are the reduced stiffness and mass metric. C is a third order tensor due to the advection operator in the Navier-Stokes equations. And you're just solving this reduced ODE, where there's only capital N unknowns. So we have gone from mathematical model, which is Navier-Stokes plus energy equation, which has infinite many unknowns, and to forward the model, which is finite but high dimensional ODEs with 1,000 to billion unknown. and to reduce order model where unknowns is only 10 to 100. So let's look at some promise, some example where reduced order model is successfully applied to. So here's a 2D flow past a cylinder at Reynolds number 100. And we consider a reproduction problem, meaning that the ROM is deployed or is tested at the same Reynolds number and time interval as of the forward model. And we see that with 20 mode, it's able to reconstruct the velocity field and the total drag on the cylinder. And more importantly is that in terms of the solve time, you see a huge difference. So for the forward model, it requires 30 minutes to run for 500 convected time units. And whereas for reduced order model with 20 mode, it takes 20 seconds to run 10,000 convected time units. Another example is a parametric problem where the reduced order model is used to make prediction at other parameters. So the process, this process is fast because we simply change the parameter in the reduced ODE and no need to go back to the forward model level. So everything is independent to the FOM degrees of freedom. And the first example here I'm showing is, again, 2D flow past a cylinder, where we monitor the variance of the drag coefficient and use that as a criteria to determine the critical Reynolds number. So we want to use the reduced order model to identify or to estimate the critical Reynolds number. And for variance larger than 10 to minus 10, we identify the flow as oscillatory flow, and below is steady flow. And with the forward model, which is shown in the black curve here, we ran through Reynolds number from 20 to 100, and we found the critical Reynolds number estimate by the forward model is like 47. And for the reduced order model, we use data at 40 and use data at 40 to build the reduced order model and do a same parameter sweep. And the estimate critical Reynolds number is around 40, which is pretty good with just one anchor point. Another example here is the Orr-Sommerfeld problem. So this is a classical problem where people use to study the evolution of small amplitude disturbance in channel flow. And from linear stability theory, you can find or you can derive the critical Reynolds number is about 5,700, 72, and 72. And with the reduced order model, we built the reduced order model at Reynolds number 7,500. And we run through the parameter space from 5,500 to 7,500. And we measure the energy of the perturbation mode. So on the y-axis is here's the mean energy of the perturbation mode. And if it's below 1, that means the disturbance decays. And we use this to identify the critical Reynolds number. And compared to the result obtained from the theory, we see that reduced order model can do a pretty remarkable job in estimate the critical Reynolds number with just one anchor point. But however, things are not that simple, and most of you should probably know this. For higher Reynolds number, not even turbulent yet, the ROM can become unstable and produce unphysical solution. And if your code is working, increasing the number of modes should recover the accuracy. So here's a 2D legitimate cavity at Reynolds number 30,000. You see that with GROM with 100 mode, we can pretty much reconstruct the forward model. However, you have to be aware that there's a tensor contraction cost, which scales like n cube. So 100 mode should probably fine, but how about turbulent flows? So here is a 3D turbulent channel flow at Reynolds number around 3,100, which is about RE tau 180. And you see that even with 300 mode, it is far away from the forward model. So the magnitude is way off. So we definitely need stabilization method and cost reduction. So here's my, well, basically my PhD work. So the way I think, there are three challenges in developing model order reduction for turbulent flow. Challenge one is to develop efficient and accurate ROM for turbulent flows, and especially for long-term prediction. So that's most like engineer who's working on turbulent flow are interested in long-term prediction. And challenge two and three is not, challenge two is to develop efficient PMOR for unsteady buoyancy-driven Navier-Stokes energy equation. So we have, in my PhD, we developed a parametric PMOR, error decay PMOR using average residual, and was able to capture the bifurcation and predict QI within 10% error. And the third challenge is to mitigate the tensor contraction cost, which scales like NQ, to enable larger N values for turbulent flows. And in this paper, we show that GROM with tensor decomposition without sacrificing too much of accuracy to obtain a compression ratio of at least 30s. So those are the the work I've done in my PhD. But in today's talk, we're focused on challenge one, which we'll focus on regularization method for turbulent flows. So we'll be talking about three regularized reduced order models. The first and the second are the Ray and EFR. So the Ray ROM, if you look at the reduced ODE on the right-hand side, it's pretty much same as the GROM, but we have the vacuum field being filtered. And for the EFR ROM, there are three steps. In the evolve step, it's a standard ROM for Navier-Stokes is soft. And in the second filter step, we apply a filter F that we'll define later and it's applied to the solution that we obtain from the first step. And in the relax step, there's a convex combination between the unfiltered and filtered solution. And in this paper, we propose time-relaxation ROM, which is a new reg ROM. And the idea is to add additional dissipation characteristics by relaxation parameters and the difference between the unfiltered and filtered solution. So the remaining part is to define what's the ROM spatial filter, F. And in this paper, we investigate two ROM spatial filter. The first one is called differential filter, which is denoted as DF. The other is called higher order algebraic filter, denoted as HOAF. So in the differential filter, we're solving a Helmholtz problem, but of size n by n. So it's just a very small system. And one nice thing about differential filter is that it has a corresponding weak form. For the higher order algebraic filter, the system is similar, but now we have a power of m in both filter radius, delta, and a stiffness matrix A. And the reason why we call it higher order algebraic filter is because it's hard to write down the corresponding weak form. But the point here is that filtering in the ROM is inexpensive. So you're just solving n by n system. And that cost is still below the tensor contraction cost. And we further studied the ROM spatial filter in the POD setting. Specifically, we want to know how each POD basis is affected by the ROM filters. So the procedure is as follows. So we fix the filter order M. And for each mode, we construct an input coefficient vector U, where it's 0 everywhere except 1 at the ith index. And then we solve the reduce the filter system, and with this delta here. So delta can be arbitrary, but we just happen to choose this one. And the coefficient, like the output coefficient UI, indicate the amount of damping in the ith mode. So we did this for 4 filter order, and from mode 1 to mode 100. And here's the result we got. So the blue are the filter coefficient with m equals to 1, and the purple are the filter coefficient with m equals to 4, and the black is just the input coefficient, which is all 1. And so if you compare to what have been studying for the model level, in 1999, Mullen and Fisher have this transfer function for the Fourier coefficient. So on the y-axis is the filter Fourier coefficient magnitude, and you see that there's and they're doing for m equals to 1 to 4, which is of course same as what we did in the POD setting. And you see before this vertical line, higher order has less damping, and after this vertical line, higher order has a sharper damping. And the cross section is about 0.5, and which we also found a similar behavior in the POD setting where the cross section is about 0.5, and we see that before like on the left side of this vertical line, a higher order filter has less suppression, and then on the right, higher order filter has more suppression. And the fact that the curve intersect at near I equals to 15 indicate that mode number less than 15 have characteristic length scale greater than the delta we choose here, which is 0.08. So we further investigate the physical space effect of the round spatial filter. So we consider the 100th POD basis function, and then we reconstruct the filter basis function with the filter coefficient. So from here, I'm showing m equals to 1 to m equals to 4. And indeed, we see that with m equals to 4, the velocity field or the basis function is smoother compared to m equals to 1. So in this paper, we consider turbulent channel flow at 2 friction Reynolds number, one at RE-tau 180 and one at RE-tau 395. So 180, there's around 4.3 million degrees of freedom, and for 395, there's 20 million degrees of freedom. We verified for the model by comparing the root mean square of the velocity with Moser's and Vermont's data. So the result here basically, it matched with the reference data, and the result here showed that our FOM is indeed DNS. And I just want to mention one nice thing here is that with NEC-RS, you can now simulate 500 convective time unit within 90 minutes for turbulent channel flow. So our quantity of interest is Reynolds stresses, and particularly the normal stress and shear stress. So the normal stress is U prime, and the shear stress is U prime, V prime, where the U prime, the prime is the velocity fluctuation, and the angle bracket here is the average operator over X and Z, which are the homogeneous direction, and the time T. And the main contribution, so the reason why Reynolds stress is important is because it's a main contributor to redistribute momentum in turbulent flows. And that's the reason why we're seeing many interesting phenomena such as sediment transport in rivers, dragging airfoil, dispersion of pollutants. And another aspect is that for experimentalists, it is not always the case that they can measure the stresses near the wall. So many times they have to take the Reynolds stress away from the wall and do extrapolation. So it would be nice if they have a model which can they can use to predict or even reconstruct the stresses near the wall. And so we use those two, the normal stress and shear stress, to evaluate the ROM performance. In particular, we look at the relative L2 error between those two stresses with respect to the forward model. So the quantity with a subscript R is the ROM Reynolds stresses, and which is defined below here. And if you look closely to this formula, it requires assistant POD basis function, which is not efficient. So it requires you to reconstruct the velocity field and do this square and then take the average. And for the U prime V prime, it requires you to do for the stringwise and spanwise velocity. So in order to have efficient evaluation for those Reynolds stresses, we do POD expansion for the raw Reynolds stresses. And then after you work it out, it can be written as quantities that can be computed in the online, which are the ROM coefficient quantities. And in the offline, we just need to store the quantity that is related to the basis function. And notice that you have to store, so for each y coordinate, you have to store this n+1 by n+1 matrix. So if you have, so it's a third order tensor, but it's still cheap because you don't need to, everything is independent to the forward model degrees of freedom. And in the online, once you have the coefficient quantities, you can do the matrix or the tensor contraction to get the raw Reynolds stress. Okay, so so far we have introduced 3 reg-ROM and the ROM filter, and also describe the QOI that we're looking at. So now we're going to show the result of our study. And this is, so I have a trial 1 here. So bear with me, later you will see why I call this trial 1. So initially we have the training data. We have 2000 DNS data collect over 25 convective time unit, which is about 4 flow-through times. And so here below, I'm showing the relative error in the Reynolds stress for the Galerkin ROM, for the array, and for 3 reg-ROM. And the black is the projection. So what that means is the ROM projection Reynolds stresses, where the formula it's defined as here. So what we're doing is we take the snapshot or the forward model solution, we project onto the given ROM space. So now we have a project velocity field, and we have, let's say we have 2000 of them, and we reconstruct the statistics using those 2000 snapshot. And that is how we get the ROM projection Reynolds stresses. So we see that from this plot, we see that convergence in the GROM and the ROM projection. So as the number of mode increase, you see the arrow initially is about like 50%, well, 100%, and then we can reach to about 0.1% error with 300 mode in both the Galerkin ROM and ROM projection. And for with reg-ROM with optimal parameters, we are able to achieve an accuracy of 5% with number of mode less than 100. So we further test the ROMs for prediction. So here is a similar plot, but for predictive regime, where we have additional 75 convective time units. And immediately you see that the blue curve is now way off. So the arrow with 300 mode is like 3000%. And with the projection, now it's like 70%. So what the fact that we have 70% in the wrong projection just says that the training data that we have is not able to represent the data outside the training window. However, with the RAG-ROM with optimal parameters, we're still able to reach pretty decent accuracy, which is 20%. And similar accuracy was observed in RAG-ROM for predicting an additional much more longer 500 convective time unit. So it seems like RAG-ROM works, but we found that the optimal parameter is sensitive. So what we did is for each, let's say we fix a n-val, which is the number of POD mode, and we find the optimal parameters, meaning the optimal filter order, filter radius, and relaxation parameter that minimize the error in the Reynolds stress. However, what we're doing is for the predictive regime, we were tuning the RAG-ROM with the testing data, which is not valid. And what we should do is use the optimal parameters found in the training window. So we can tune the RAG-ROM in the training window or the training data because we have the data, so we can do that. But what we should really do is to use that optimal parameter found in training window for prediction. And once we did that, we found the error is no longer 20%, but 1,000% error. And it is because you could see the plot I'm showing below is the optimal filter radius for each n-val. And you could see that the location is different in the reproduction regime and the predictive regime. So that's why, so it's sensitive. So it took us some time to fix this. And eventually we found that the training window matters for RAG-ROM. So instead of using 25 convective time unit, we instead rebuild our model with 500 and 1,000 convective time unit for RETOL 180 and 395. So those time interval or the time window is roughly when the turbulent statistics converge. So it takes 500 convective time unit for the turbulent statistics in the RETOL 180 to converge, and for 395 it takes 1,000 convective time unit. So with this new training data, we found that the optimal delta or the optimal parameters in the reproduction regime is also optimal in the predictive regime. So below is I'm showing the error behavior versus delta in the reproduction regime, and the optimal filter radius is about like 0.14. And we also did this for the predictive regime. And you see that they have the filter, like the optimal filter radius is about the same location, 0.14. And we have similar result for the relaxation parameters. So with this new training window or training data, we compared the 3 RAG-ROM with the optimal parameters. So what we did is for each RAG-ROM, we consider a quite big parameter space where the number of mode is from 10 to 100. And for filter order, we consider from 1 to 4. And differential, the filter radius is from 0.01 to 1. So, and for relaxation parameter, we start from delta t because that's the typical value that is used in the forward model for EFR, and the upper bound is 1. So we do this, and then we find, for each n, we find the optimal parameter that minimizes the error. But now it's with respect to the training data. And in the reproduction regime or the training window regime, for both Reynolds number, we find time relaxation ROM is the most accurate model. And for the predictive region, where we have additional 500 convected time unit, the time relaxation ROM is also still the best model. And when we also compared the performance of RegROM with differential filter and higher order algebraic filter, and we found that from all the, like in the reproduction and predictive regime and in both Reynolds number, we found differential filter, which correspond to m equals to 1, is the most accurate. So I was just showing the error behavior, and here is I'm showing the total, well, the Reynolds stress, but also the total and viscous stress. So the viscous shear stress is just the derivative of the average velocity in y direction and times the viscosity. And the total stress is just the viscous shear stress plus the Reynolds shear stress. And here I'm showing for the Ray ROM, EFR, and time relaxation. And the reg ROM is showing the reg ROM result is in blue, and black is forward model, and the red is ROM projection. So what we found is that for the viscous shear stress, you could see the reg ROM captured pretty well. Pretty much lies on the forward model. For the Reynolds shear stress, we see that time relaxation ROM is the best, whereas we see over prediction in the Ray ROM and EFR ROM. And another interesting thing is that for the ROM projection, which is the red, if we look at the solid reg curve, which is the Reynolds stress, you see that it's way off compared to the forward model. So what that means is that the data that we have is still not fine enough. Like we don't have enough data to represent. But even with this, the reg ROMs can still do pretty good job. And this is just a similar result, but for a higher Reynolds number. So now we can clearly see that the Ray and EFR ROM overpredict the Reynolds stress. But for the viscous shear stress, all three models can still capture it quite well and match the forward model. And I forgot to mention, but the dotted or the dashed line is the total shear stress, and in theory, it should be linear, no matter whether it's a laminar flow or turbulent flow. And so we see that for the forward model. However, for the ROM, we see discrepancy, but that is due to the Reynolds shear stress. So what we found is that reg ROM outperform ROM projection, and time relaxation ROM is the more accurate result. It's the most accurate model, but for higher Reynolds number, it needs further improvement. So it's still not perfect. And in this paper, we also perform sensitivity study of reg ROM's performance with 2 parameters. So filter radius and relaxation. And what we found is, so there's a very more detail you can find in the paper, and I don't want to mention, like I don't want to talk about those because that will confuse the audience. But the summary is that we found is sensitive to the filter radius. So you see, for a small filter radius, we see the error is pretty much same as the G-ROM. You can think of, it's just saying that for delta up to this bell, all the mode has characteristic length scale less than the delta here. So that's why there's no effect on those ROM solution. And if the delta is too large, your system becomes too dissipative and you got all of one error. And there's a minimum in between, and which is quite sensitive. Like if you increase delta a little bit, your error could just becomes your error is sensitive to delta. And we also found sensitive to the relaxation parameters. So for EFR, here we have 4 relaxation valve. And we found that, so you could see it's sensitive to the relaxation parameter, but we also found that chi equals to delta t yield the best result, and which is similar to the what was discovered in the forward model. And for time relaxation, it's less sensitive than relaxation, but you still see some sensitivity. Okay, so those are the results for the turbulent channel flow. And here I'd like to mention another application that we have applied RegROM to, and it's an ongoing work. So it's a T-junction test case where we have thermal mixing take place for liquid with different temperatures. So we have a cold inlet and hot inlet. And in the junction, there's start the mixing. And in the outlet, you don't see that much mixing. So this is a benchmark problem in nuclear engineer safety. And they want to study thermal striping at the pipe wall. On the right, I'm showing the temperature history for the forward model at different locations from the mixing, which is the junction, to the outlet. So you see those irregular temperature behavior close to the junction. And then as you move toward outlet, it becomes less irregular. So we built the RegROM, or we built Galerkin ROM and RegROM using the data denoted in the red vertical line here. And the blue, we use the ROM to reproduce and predict the temperature history at several locations. So from mixing to outlet, and you can see that GROM, which is the blue here, with 250 mode, is definitely not stable, and it over predict, like it couldn't capture the temperature history. Whereas with the 3 RegROM, not only it can reconstruct the temperature history, but also outside the training window, it can also kind of capture the temperature behavior. And those are just with 100 mode. Okay, so before I conclude the talk, I want to point out emphasize the workflow and practical consideration of applying model order reduction to turbulent flow, and what just happened in this stage. So when we go from forward model to the reduced order model. So it consists 2 stages. In the online stage, this is like everything is fine because it only depends on the reduced order model degrees of freedom. So once you load the ROM operators, you can solve your reduced order model on your laptop or workstation. However, the problem is coming from the offline, where everything depends on the forward model degrees of freedom. And normally there are like 3 steps. So in the first step is where we generate the data, the forward model data. And for a typical CFD code, it's around, the memory requirement is around 400 vectors of size billions. So that is fine. You can run that even like on the supercomputer. That is the memory requirement is fine. For step 2, which is where we construct reduced basis. Here we use which is called NAGROM, a MOR framework for NAG 5000 and NAG RS, and the memory requirement here becomes 1,000 to 4,000, depending on the size of the snapshot matrix. So for 2D and small 3D problem, you won't see like this bottleneck. But if you go to 3D turbulent flow, for example, when I was doing turbulent channel flow at 395, you get into this bottleneck where either you don't have resource or you need a lot of computing power just to get the reduced basis. So the memory is really intense on step 2. And in step 3, where we construct operators, is less intense and normally just require capital N vectors of size billions. So as our project started 5 years ago, we didn't realize this, like the second step bottleneck. And like past 2 years, we were struggling at this stage. So I just want to bring this up to you. If you're applying like reduced order model to turbulent flows, this is definitely something you might need to keep in mind. So the summary and future work. So we introduced a new time relaxation ROM, and we found it's more accurate. Was the most accurate model compared to the 2 existing ROM, the reg ROM in turbulent channel flow. And we found that the training window size matters, and it improved the reg ROM's optimal parameter robustness. So we can use that to do prediction. And for long time prediction. So what I was talking about is like for 500 convective time units. And we found reg ROM are sensitive to the filter radius and the relaxation parameters. And the ROM filter that I demonstrate behaves similar as the Fourier setting. So higher order ROM filter dampens the higher index mode more and less on lower index mode. And less is the memory for reconstructing the reduced basis is critical when you're working on turbulent flow. And one future work we have in mind right now is that we want to do numerical analysis for reg ROM parameters, so that the optimal goal is to we don't need to do like tuning. Right now, we need to consider like a relative large parameter space to find the optimal parameters. Yeah, and last is I want to promote like our like a software which is called NEC-ROM. It's a MOR firmware for NEC 5000 and NEC RS developed by me and Kaneko Kento now at MIT. So if you are interested in our reduced order model software, please take a look at it. Thank you.
Very nice, Ping-Hsuan. Thank you. This was very nice. I didn't know about the NEC-ROM. Very interesting. Okay. So this is interesting stuff. Okay. So if anybody has any questions for Ping-Hsuan, please raise your hand or just unmute yourself and ask questions. I have several, but maybe I can start. Okay, so let me ask you a question. So there was more of clarification. So I think on slide 26, you said that the reg ROMs outperformed the projection, and
yeah,
right. So can you explain a little bit what you mean by that? I mean, what's going on there? So what is
yeah, so yeah, here we need to be a little bit careful because normally when we're saying ROM projection, like that's the projection. So we should expect like why like we can expect like ROM is better than projection, but it's because we're looking at turbulent statistics, and here's the Reynolds stress. And so in that sense, the ROM projection is just optimal in the sense of reconstruct the velocity field. It's not like statistics. So if we use the best like approximate velocity field, it doesn't imply that we'll get the best turbulence statistics. Yeah, but we see that reg-rom can still, outperform like those, which is nice.
I agree. And but could it be also with the fact that maybe sort of the reg-rom level, so we do some filtering and that's the, beneficial, maybe that's something that maybe it's not necessarily taking care of the projection level. So, okay. But what you said makes sense to me, Ping-Hsuan. So this is right. I mean, so you're saying that if you have the best velocity, so like now we're looking at statistics, so that's a little bit different. So one is to be careful. Very good. Okay. All right. Any other questions for Ping-Hsuan? I can ask one more. Also clarification. So, on the last couple of slides, you pointed out, you emphasized the issue with turbulent channel flow, and there is the second step that you're constructing the basis that you said that this is actually right here. So, why is that, and how do you guys have like plan? I mean, so do you guys have like solutions of how to tackle this, or?
So there we have right now we have two solutions to tackle this problem. So the first one, the reason why we have this intense memory in step 2 is because we're using POD to construct the reduced basis. So when you're doing POD, you need to store the snapshot metrics. Your computer need to store the snapshot metrics. So that's why it has this intense memory. But the first solution is to do incremental SVD. So people have been using that to do incremental SVD. So especially they can do it once you get the FOM data, and you can update the SVD and update the basis function. So that is one approach to avoid having intense memory. The second solution is, which is proposed by Kento, is to we rewrite the procedure of forming the Gramian. Like we do it element-wise base, so that the memory requirements is less. We can do this on workstation, but it takes longer time. So it's less memory intense, but it takes longer time. Yeah.
I see. Very nice. Thank you. That's very nice. Okay. Any other questions for Ping-Hsuan?
I guess I can ask about
yes.
In the final slide at some point you mentioned that tuning is still somehow of an issue, and then this numerical analysis could help. So do you have a specific insights on what could help?
So finally, I don't. Well, so
can I help here?
Yeah.
Can I help here?
I'll let Chai.
Yes. So this is we discussed this before. So we're working together on a paper to provide this type of scalings. So that's with Jorge. Jorge is also in the audience. Okay. Now, so what is the idea? So the idea, Francesco. So it's like what we've also discussed. So the idea would be, can we look at all the parameters that come into play? And I know that this sounds like a lot, but so we look at the spectral element form parameters, and we look at the ROM parameters as well. So spatial time discretization ROM parameters, and then we look at the asymptotic error bounds that we're proving. And then we try to balance the different parts of the right-hand side, so that maybe this can give us scalings for exactly those parameters that are quite sensitive, like delta and chi. Because the idea would be, okay, so I find the best parameter delta and the best chi parameter for this turbulent channel flow simulation. Then I'm going to the turbulent junction problem, and then I have to recompute to retrain my, and even so once you change the problem, even if you change the setting, you have to recompute those optimal parameters. And our hope is that maybe we can get something like delta scales, like the spectral element mesh size to some power or something like that with a constant. That's fine, but at least that's some, is one parameter that you have to kind of like it's like in order one type of parameter. You don't have to investigate over orders of magnitude type of, because you don't know what delta should be like in principle. And so that would be the idea. And we're still working on the paper, so we don't have the paper yet, but we're getting there.
Okay, great. Thank you.
Thanks, Francesco. Great question. This is an excellent question.
Thank you,
right.
Tsai.
So anybody else? We got some appreciation in the chat, so that's good. Well, if not, so let's thank again Ping-Hsuan for this very nice talk. And he's very, so he said that he's very open to getting emails from you. So if you have any questions about turbulent channel flow and what has to be done, he has a lot of experience and a lot of negative stories to share. So please email Ping-Hsuan, and he's gonna honestly tell you the ordeal he's gone through with the turbulent channel flow, which I think is an excellent test problem. If you really have code, the ROM code you want to test, that's a perfect test problem, because chances are it's gonna fail. So it's a very hard problem. So anyway, so if no more questions, so we'll see you guys. We'll see everyone on next Tuesday at the next NAGRAM seminar. Have fun and see you soon. Thank you, Ping-Hsuan.
Thank you all.